So, our speaker today is Ralf Meyer, and his title you can see there is Cuntz-Pimsner algebras and Groupoid models for Groupoid correspondences. Please, Ralf, go ahead.
Yeah, thank you for this invitation to speak in this seminar. So today I want to report on some recent work, which was mainly in the thesis of Celso Antunes. And then there is also some ongoing work by myself and Giles de Castro from Florianopolis. Which is about morphisms between, well, groupoids underlying graph algebras and similar things. So, many interesting C-star algebras are built from some combinatorial data. And maybe the model for this would be graph C-star algebras. Where you start with some combinatorial data, namely a graph, and out of that, you make a C-star algebra somehow. And this was arrived at by generalizing the famous Kuntz algebras. These graph C-star algebras are also known to be groupoid C-star algebras. And in the very first papers involving Jean Reynaud, this was indeed one of the main tools to study them. Because if you know that a C-star algebra is a groupoid C-star algebra, then you have criteria, for instance, for when it is simple, when it is purely infinite, these kinds of things. So it's quite useful to know whether a C-star algebra is a groupoid C-star algebra. One thing that you might like about graph C-star algebras is that they are defined by some nice generators and relations. So this is one of the approaches to them. So this specifies a universal property for them. And one question I want to answer positively today is there a similar picture or a similar description for the groupoid? So I mentioned that graph C-star algebras are groupoid C-star algebras. So you can describe a certain underlying groupoid, and you can use that to study them. But the definition of this groupoid might seem somewhat ad hoc. So you look at paths in the graphs, and in some cases you need certain finite paths and then infinite paths, and to put them together, put on some suitable topology, and then you also have to define arrows on these things. So the definition of the groupoid, this might seem to be complicated. And so you might want to study this groupoid not directly by its definition, but maybe also like a graph C-star algebra by specifying some generators and relations for it. And then you might wonder, what might this actually mean? So can you define groupoids by universal property? And the answer is yes, you can. And I will explain how this works for graph C-star algebras and similar things. Graph C-star algebras have been generalized in various directions, and you might explain these by putting adjectives on. For instance, there are topological graphs. So this just means that you put topologies on the edge and vertex sets and assume some properties of the range and source maps, and this will give you a topological graph. Something else you could do is self-similar graphs. these were defined by realizing that self-similar groups could be combined with graph C-star algebras in a certain way. So it was realized by Excel and Pardo that the self-similarity that you can see in the group case also makes sense in a more groupoid-like situation, and this was leading to the concept of a self-similar graph. There are actually some slightly different variants of this definition, depending on what conditions you assume for the range and source maps in this graph. I think I won't focus on this issue. And of course, you can also combine them and look at topological self-similar graphs. I think these haven't been studied that much. I would argue today that this is more or less the same thing as the groupoid correspondence. So a single groupoid correspondence on an étale groupoid is how I would define a self-similar topological graph. And so, as you see from my title, the goal of this talk is to attach C-star algebras and groupoids to this data. And of course, the point would be that the groupoid C-star algebra of this groupoid, which I call the groupoid model, is also the C-star algebra I want to look at. And the C-star algebra in question is always the Cuntz-Pimsner algebra of a certain C-star correspondence. And this gives us another nice picture how we can look at a graph C-star algebra. So it is always a Cuntz-Pimsner algebra. So we have three different ways to study a graph C-star algebra. Using the groupoid, using its genders and relations, or using the C-star correspondence and then the Cuntz-Pimsner algebra. And depending on which point of view you take, you have different results that you could use to study them. For instance, there is already by Pimsner a nice result about the K-theory of Cuntz-Pimsner algebras, which is, well, the simplest way to compute the K-theory of graph C-star algebras. For simplicity, the results for C-star correspondences and Cuntz-Pimsner algebras are a bit less good, I would say, than for groupoids. Well, there's results for both cases. I would prefer to work with the groupoid results because I'm more used to them. And of course, if you want to construct some explicit representations, then genders and relations are your friends, so you want to use that. And that's, of course, an important feature of this class of algebras, that you have different descriptions for them. And similarly, for these topological self-similar graph C-star algebras, or the C-star algebras of groupoid correspondences, it is important that you have two different ways to describe them, as Cuntz-Pimsner algebras of a C-star correspondence or as a groupoid C-star algebra of a certain groupoid. And then this groupoid also has a universal property, which is somewhat analogous to that which a graph C-star algebra enjoys. Okay. Nothing in the chat. So maybe let's, before I continue, give you an idea about this universal property that a groupoid might have. So this is the ongoing work with Giles de Castro I mentioned, and I think it's a quite cool result, and it's somewhat surprising that it hasn't been noticed before, maybe. So let's take a graph. So a graph has certain vertex, has a vertex set, and it has edges. I call them E and V, and then there is a range in the source map. And then for the C-star algebra, you take generators, which are projections PV for the vertices. And you take partial isometries, and I prefer to call them TE because I use S for the source map, which are partial isometries. And then you have certain relations. So the relations are that these PVs are mutually orthogonal, and of course projections. And then TE star TE is the projection for the source of E. And for a regular vertex V, you assume that the sum of these range projections of the TEs is the projection for this common range of all these edges. And then if V is not regular, you at least assume that the TE star so these range projections are supposed to be below the projection for the range vertex, and they are supposed to be mutually orthogonal, even if this vertex is not regular. Regular means that there is only a finite but non-zero number of incoming vertices. So this means the range preimage of V has a finite number of elements, not zero, not infinity. Okay, now this universal property says that if you want to define a homomorphism from a graph C-star algebra to another C-star algebra, you have to specify such projections and such partial isometries in the target satisfying these relations. And now imagine that you have a groupoid and you want to define a map from the C-star algebra of this graph to the C-star algebra of a groupoid H. So you have to produce these projections and partial isometries in the groupoid C-star algebra. And you might wonder, where can you get projections in a groupoid C-star algebra in a somewhat geometric way? And there's a nice translation using bisections in the groupoid. So a bisection in H this means an open subset of the arrow space, and R and S are injective on this. And bisections can be multiplied. So if you just take the pointwise product, as far as it's defined, it's again a bisection. Also, bisections have a source and a range, just the image under these range and source maps. And if a bisection is also compact, not just open, so a compact open bisection call it maybe U. This produces a characteristic function in the C-star algebra of the groupoid, and that is a partial isometry. And if your bisection is contained in the unit space, then this is actually a projection. So this would be the thing that corresponds to projections. So the translation here would be that you have subsets, maybe I call them omega V in H0, which are compact open. And here you have some bisections, also compact open bisections. And then the relation that you have here, these translate to, well, here you would talk about the source of the bisection being omega of the source of E. And here this direct sum relation just becomes, there's a disjoint union of these ranges of the TEs, and that's supposed to be omega of V. I'm not sure this is still readable enough for you. I think I should maybe write bigger.
I can read it.
Okay. Very good. So you can just translate the defining relations of the graph C-star algebra into bisections and compact open subsets of the groupoid. And clearly, using this fact that if you have a compact open bisection and its characteristic function is a path isometry, if you are given this data, then this produces a star homomorphism from the graph C-star algebra to this groupoid C-star algebra. And now the nice thing is that there is a category of groupoids in which the arrows from the graph groupoid to this groupoid H are exactly these families. So these omegas of vertices and t's of e's with these conditions, they are in bijection to the arrows in this category of groupoids from the graph groupoid to the groupoid H. But this requires some more room to write up. I should be more precise and say that I'm talking about étale groupoids all the time.
You write actors.
I'm writing actors.
Yeah, that's what I understood.
Actors. So that's not a very common category. I have to define what I mean by that. But there is a certain way to turn groupoids into a category. And in this category, the arrows from the graph groupoid So there is a nice category of groupoids where the arrows are such that an arrow from the groupoid underlying a graph C-star algebra to another groupoid H is just such a family of bisections omega, compact open sets omega V and bisections TE with the conditions I just explained.
So how do you write CK2 in the language of groupoids? Because you need a sum, right? Or are you using some
the sum becomes a disjoint union. So you have a sum of projections, which means a sum of compact open sets.
You change, and this is you just switch blackboards, but
yes,
camera is still on the previous blackboard.
Yes, I can switch. So I indicated here this disjoint union symbol, which might be hard to read for you.
Okay.
So the ranges of the TEs are all disjoint, and their union is omega V.
Okay.
And here, of course, this is just an inclusion. The range of TE is contained in omega of RE. And then mutually orthogonal becomes mutually disjoint. And of course, the disjointness is also a consequence of this relation, so it's clear that they should be disjoint. Okay, I should now briefly mention what actors are. So given two groupoids G and H, I want to look at an action of one groupoid on the arrow space of the other, and it should commute with the right multiplication action of H on itself. That's what I call an actor. This is not the same as a functor. It has certain advantages if you like C-star algebras. So an actor between étale groupoids, so today I think all groupoids are étale, then it induces a morphism so from C star G, and morphisms, I remind you, go to the multiplier algebra. Inside the actor, there is also the class of proper actors, and I should add the adjective proper here to make this result really correct. So the actors, as they're defined here, would allow you to go into the multiplier algebra. So they would give you projections in the multiplier algebra. And properness just means that a certain map is proper. So the action has an anchor map.
So would it be fair to say that it is a correspondence in which the space is the arrow space of the second, of the target groupoid?
Yes, that's another way. If you know what Groupoid correspondences are, it's a special kind of Groupoid correspondence. So if you have an actor, you have an action on H, this must have an anchor map going to G0. This anchor map factors through the orbit space for the right multiplication action, because it is invariant under it. And that orbit space is H0. And if this map from H0 to G0 is a proper map, then this goes into C star of H. And as Willy pointed out, an actor is a special kind of groupoid correspondence. So more generally, there is only one nuance. I like to choose the opposite direction for groupoid correspondences, because I like the source to be on the right and the range on the left. So it makes more sense for me to let the Groupoid correspondence X go from the right to the left. So this is a space X. So in a Groupoid correspondence, I have a space X on which the groupoids G and H act on the right and on the left. And one of the actions, namely the right H action, is assumed to be free and proper. And also the anchor map of that action is supposed to be a local homeomorphism. And beware that in different contexts, you might have seen somewhat different combinations of these properties. So in particular, this is not the same as what Hilsum and Skandal is considered. And a Hilsum-Skandalis morphism wouldn't induce such a morphism of C-star algebras, for instance, so you couldn't use it in that way. It's different in the fine print, so you have to read carefully what they defined and see that neither is contained in the other, so they are really a different set of conditions.
May I ask a silly question?
Sure.
I naively thought that given that groupoid correspondences can be composed, that a Morita equivalence, and that they are like bimodules, the Morita equivalence should be an invertible groupoid correspondence.
That is true.
But
even
then
better.
But is this the same as the inclusion of so somebody told me that Morita equivalent, so is the kind of correspondence is generated by an inclusion of an open subset where the quotient of the unit space by the action of the open subgroupoid is so has the same quotient.
So now you're talking about
what the reference, what the relation is with these other things. So I couldn't figure out how to write this in terms of correspondences.
Okay, so first of all, a Morita equivalence is the same as an equivalence in the bi-category of groupoids. At some point, I should tell you what bi-categories are, but since you asked now for this, maybe let's do it in a hand-waving way. So this means that you have groupoid, so groupoid correspondences can be composed. You just use the same recipe which you use for Morita equivalences of groupoids, and it still works in this generality and gives you again a groupoid correspondence. And if you assume that a groupoid correspondence has an inverse under this composition, so that X composed with X inverse is isomorphic to G and X inverse H is isomorphic to H, as a groupoid correspondence, then it must be a Morita equivalence. Now, this other picture which you mentioned, I suppose you want to talk about, well, my colleague Chen Changzhu might call these ANA functors. I wouldn't use open subsets, I would use something else.
Open subset.
So if you have a map from some space Z to the object space of a groupoid, maybe call it P, then you can make a new groupoid, maybe I call it P star of G. And its arrows are like this, so you have 2 points so you have 2 elements of Z and an arrow in the groupoid G, so that the range of G is Z1 and the source of G is Z2. So this is a recipe for making a new groupoid. And this groupoid comes with a canonical projection to G. Just forget about these Z's here. And this is a typical example of an equivalence, because you have just multiplied the objects, but you notice that different elements of Z with the same image in G0 are always isomorphic, just put identity here. And so you have just increased the number of objects by noting objects down several times. So this is a kind of standard Morita equivalence. And I believe it is true that every Morita equivalence can be written as a composite of such things. So you could find something like P star of G is isomorphic to Q star of H, where you just pull back both groupoids to the same space. And I guess if you have the equivalence, then you just take the equivalent space X here, use the range and source maps, and somehow identify these groupoids. But I didn't prepare this, so you better look this up.
So one question. So suppose I have an open subgroupoid of a groupoid, right? With the same unit space, and such that the quotient of the unit space modulo the open subgroupoid is the same as the quotient of the same unit space modulo the whole thing.
Yes.
So would this inclusion of the open subgroupoid in the groupoid be a Morita equivalence in your...
Okay. It would, yes. But that's a different case once again. So this wasn't these ANA functors then. By the way, how much time do I have?
20 minutes. Sorry for I interrupted you.
Well.
But I mean, I didn't want to miss the opportunity of...
yeah, I can explain this
I
quickly.
always wanted to know and haven't dared to ask before.
It doesn't take long to explain, but I won't give you the proof, at least as an exercise.
Yep.
So if U in G0 is open, then you can take GU to be all arrows in G
camera.
with source in U.
Would you please switch
now I'm on this blackboard, that's stupid. So you take this subset, all arrows with sources in U, and then G is acting on this on the left in the obvious way, and on the right, you can only multiply with arrows which have both source and range in U, which is this thing here. And if the orbit of U is everything, so if G times U, let's say, is all of G0, then this is a Morita equivalence. And I'm not sure whether you can get all of these equivalences in this fashion. I don't think you can, but in particular, you can't really change the topology of your object space. Like if one of them is just a point, how could you go from that to a group which is topological, not just discrete or something? I don't think you can. So, but at least this gives you some examples of Morita equivalences.
Okay, thanks.
Okay, so I should now turn back to my actual topic. So I have defined for you what groupoid correspondences are. And this also gives you the data which you can use in my machinery. And I mentioned that if you have an actor, that's a special case of a groupoid correspondence. And an actor gives you a morphism of C-star algebras. Similarly, if you have a groupoid correspondence, then you can attach to that a C-star correspondence between the groupoid C-star algebras. So here I have G and X and H, and here I have C-star of G acting on the left on a Hilbert module C-star X over C-star H. So using that the right action is free and proper, and its anchor map is a local homeomorphism, you can define a Hilbert module structure starting with continuous function with compact support on X and then taking a suitable completion. And then there is a left action of C star G on that. You might have seen this in connection with Morita equivalences, and it's the same formulas. There's only some checking to be done to see that you still get a C star correspondence, which is less than a Hilbert bimodule, if you start with a groupoid correspondence. Let me highlight here that I need non-Hausdorff groupoids in this theory, because these groupoid models might well turn out to be non-Hausdorff, for instance, for self-similar groups. So I should allow non-Hausdorff groupoids, and all this works for non-Hausdorff groupoids. There is a paper by Antunes and Joanna Coe and myself where we check this. So that this is a well-defined construction. Also that this is a bicategory, so groupoid correspondences. Bicategory means that there is a useful composition. Furthermore, there is another layer of arrows between groupoid correspondences. These are just maps, continuous maps, which are compatible with the actions on the left and right. And I think I want them injective for this to work nicely. Because I want to get isometries on these C-star correspondences in the end. And for that, I need an injective map here. And this construction here is part of something like a functor. But in the context of bicategories, there's some subtleties. It's called the homomorphism of bicategories, if you know what it is. If you don't know, then it's just like a functor. So it's a nice way of turning groupoid correspondences into C-star correspondences, which is as compatible with all structure as you could hope for. Okay, so if you start with a groupoid correspondence, get a C-star correspondence. And then out of that, you can make now a Cuntz-Pimsner algebra. But there is a small catch, namely the Cuntz-Pimsner algebra construction works really well if your left action of the C-star algebra is by compact operators and injective. Injective we can't control, but you don't really need it. You can still make an absolute Cuntz-Pimsner algebra if the left action is by compact operators. Another point is, to get this, I now want that G is equal to H. So the Cuntz-Pimsner algebra only exists if you have a self-correspondence. It's like an automorphism versus an isomorphism. If you just have two isomorphic C-star algebras, different ones, you can't make a cross product. We need an automorphism for that. And similarly, you need an endomorphism to make this Cuntz-Pimsner algebra. And if the Groupoid correspondence is what I call proper, meaning a certain map is proper, then this left action here is by compact operators. And then I can just impose this Cuntz-Pimsner condition for the whole C-star algebra on the left and get a Cuntz-Pimsner algebra. If that doesn't work, I should specify a certain ideal which acts by compact operators and impose the condition only on that ideal. There's a nice choice for that due to Katsura, which we always take when we make graph C-star algebras. Unfortunately, this doesn't usually come from the Groupoid side. So the setup I need is a bit more. I also want an open subset which is open and G invariant. And I want that if I take the preimage of this open subset and divide out the G action, so this is a subset of the orbit space of X. I divide out the right action, and inside I have this space, and the range map induces a map from this to U, and I want this to be proper. This map here from this space to U should be proper. That's extra data, I assume. The good thing is this open subset generates an ideal. So since it is G invariant, this restricting the source or the range to U gives the same subset. Unlike here, when it's not invariant, I have different subset. I need this notation like this. Here I get an ideal. So I get an ideal in C star G, and this acts on C star of X by compacts. Okay. And now I can make the relative Cuntz-Pimsner algebra for this ideal. So this is the kind of C star I want to look at. And the main result is this is a Groupoid C star algebra. So this is a Groupoid C star for a certain Groupoid, which I call the Groupoid model. And this Groupoid model is defined So it's defined by describing its actions on spaces. So I define what my data So the point here is that I make a category of actions of this groupoid correspondence, which also takes into account this open subset U, of course. And this category should be isomorphic to the category of actions of a certain groupoid. And in a special way, namely, I don't want to change underlying space. So I want that an action of this data becomes an action of the groupoid. And a map is equivariant for these actions if and only if it's equivariant with respect to the actions of the groupoid model. And since I have only roughly 6 minutes, I suppose I should define these actions. And that's maybe the last thing I can do.
Yeah.
So you want to have an action of G, and this has an anchor map, which I should have written down first. I always call anchor maps ray R on the left. And if I have this map, I can form this fiber product. And the action of the groupoid is then a multiplication map from arrows to Y with certain properties. And then there is also a kind of action map for this space X. And then there's a list of properties. So something like associative. So if you have an element of arrow in G and you have some element X and something in Y, we have something like this, of course, and also like this. Furthermore, you want that if you have two pairs of elements which have the same image under this multiplication map, so I write this also as a multiplication map here already, then this should imply that x1 is x2 times G for some arrow, and I think GY1 is Y2. So the only way how this can happen is in the obvious way, namely something like this here. So this here gives you some relation, and this should be the only one that you expect to have. What else do I want? One condition must involve the set U. So the condition is just that if a point in Y has a range inside U, then it should be writable in the way X times something. So if R of Y belongs to U, then it follows that Y is something like X1 times Y1 for some X1 in X, Y1 in Y. So notice that if U is everything, so it's all of G0, then this condition is always satisfied. So you just say that this map here is surjective. And in a previous draft by me, you can find this condition and used to make a groupoid model. Okay, but then there is one more technical condition. About certain subsets being closed. And in the paper, you can read up why it's necessary, why the theory doesn't work without it. And I think I don't want to spend the time on that.
Okay.
So there's also a small catch in the definition of the equivariant maps. If you have two such spaces, then there are some obvious conditions for an equivariant map. So you want to say that G times phi of X, so phi equivariant. Of course, you want that phi of G times Y1 should be G times phi of Y1, and phi of X times Y1 should be X times phi of Y1, whenever this makes sense. A less obvious condition is that the phi pre-image of X times Y2 should be X times Y1. This turned out to be crucial to get the correct definition. Okay, so with these catches, you define a category of actions of these triples. And then it turns out that there is a groupoid which has exactly these things as its actions. And of course, the groupoid is somehow generated by things in G and X and so on. Okay, now I should link back in the final words to this actors that I had in the beginning and this universal property. So this space Y could be the arrow space of another groupoid. And then these kinds of actions specify actions of the groupoid model on that arrow space. Well, to get an actor, my action should commute with the right multiplication action. But since the passage here is kind of natural, you can work out what this means for these maps, and you arrive at a nice condition, which would then give you that, in the case of a graph groupoid, the action must look like the stuff I started with in the beginning. I think really my time is up, right?
Yeah,
Otherwise, I would give an example.
But
Okay,
if you want to do one short example, I don't mind. I mean,
okay, so I have to wipe the board again for that. So let's look at a simple case, the simplest kind of graph you could imagine. Let's make the O2 graph. So one vertex, two edges. So what is G in this case? It's just a point. It's the one-point groupoid. And therefore, a G action is just empty. So it's no data. On any space Y, there's a unique G action. X, in this case, is 2 points. And, well, the left and right actions are nothing, as I just said. So it's just 2 points without further structure.
Are you saying that the groupoid of the graph is 1 point?
No. The groupoid on which I take a groupoid corresponds is 1 point.
So that's the age. The
I
groupoid associated.
might have called it H before. H was equal to G in my discussion at some point, yes. I called the groupoid model M, like model. There's only so many letters in the alphabet. And if you want to see O2, if you take the groupoid C-star algebra of this groupoid, it's just the complex numbers. I mean, it's also a group, the trivial group. Of course, you get this. And if you take the C-star correspondence for 2 points, you get C squared. Not surprising. And if you have seen Kuntz algebras, you might know that they are the Cuntz-Pimsner algebra of this particular C-star correspondence here.
Okay.
Okay, and so the action also has a map from X times Y to Y. And there is some conditions. And what you really want is, so this is 2 copies of Y. And in this particular case, it just said that this is a homeomorphism. So 2 copies of Y are homeomorphic to Y in a specific way. And of course, you can now restrict this to the 2 pieces. And this gives you 2 partial homeomorphisms on Y, which look a bit like isometries. So each inclusion is one of these 2 generating isometries, S1, S2 in the Kuntz algebra O2. And in this particular case, my U is everything, is the whole point. Otherwise, I would get the Kuntz-Toeplitz algebra, which is also interesting, but I want to get the Kuntz algebra, so I need this set. And then this map here should be surjective. And some other conditions, in particular, this condition here forces this map to be injective. And I think I leave it about this with this example. Feel free to ask me more questions about it. And I want to stop here now.
Okay, thank you very much for a very nice lecture. So, does anyone in the public have a question? Okay, so I have a small question. Is there some sort of analog of the Eilenberg-Watts theorem saying that any functor between model categories is tensoring against some bimodule that applies, I mean, in this setting, like any functor that takes G spaces to H spaces comes from a bispace or something like this, which correspondences.
That's a nice question. I tried to find such a result, but there are some topological issues with non-Hausdorffness, bad quotient spaces, so I couldn't really get anything like that. So a special case, which is, well, is more about isomorphisms. So if you know, for instance, a group is determined by its category of actions on spaces, if you remember the spaces. So if you can turn G action on Y into an H action on Y, in a natural way, then the groupoids G and H have to be isomorphic. And this is how you get this particular functor. So you don't change the space at all, and then you can, of course, do something nice. If you're allowed to change the space, I couldn't find good conditions. So the one problem is if you don't have a free and proper action, you might still try to do something like this and divide out the G action. And for instance, if the action is only proper, not free and proper, this might still be a reasonable thing to look at. And I think it will give you a nice functor with certain properties, but not all properties you want. And then you don't really need the action to be free and proper if you don't insist on this quotient to be a Hausdorff. And finding a good mix of conditions, I didn't succeed.
Okay. Thank you very much for the explanation. So, do we have any more questions? If not, I'm going to stop the recording now.